Given a surface z equals f of x, y, we will define the gradient of z. So the gradient is, we uses this symbol, which looks like a capital delta upside down or a triangle upside down. And I'm just going to call it the gradient symbol. So the gradient of z, which is the same thing as the gradient of f, which is a function of two variables, if the function, the original function is a function of two variables, is very easy. It is a vector, first of all. The first component is the derivative of the function with respect to the x variable, or the first variable, whatever it may be. And the second component is the derivative with respect to the second variable. So there's a couple ways to write this down, f sub x. And then I'm running out of space up there, so I'm going to put it up here, f sub y, and then close the parenthesis. So this is the vector. Sorry to move that up there. So that's it. That's the gradient. And essentially, all it is telling us is the slope of the function of the surface. Remember, we got a surface going on the x direction and on the y direction. So if we had something like this, and this was the x direction, this would be the first component. The slope, rather, of this is the first component, and the slope of that is the second component. Now, you may be thinking, wait a minute, that's 90 degrees, so aren't they going to be like 0 and infinity? No, 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 no. The slope relative to the z-axis. So if you go in this direction, we have a slope. If you go in this direction, there's a different slope relative to the z-axis. So let me write that down. So this is the slope or rate of change of z relative to x. So as you move x, yeah, slope, I shouldn't put off of just slope z over x, and this guy is going to be the slope z over y. So as you move on the y direction, you're going to get one slope. If you go on the x direction, you're going to get perhaps, very possibly, a different slope. Yeah. Let's do some examples. Example 1. Let's say f of xy equals x squared plus y squared. That also means that z is equal to x squared plus y squared. So the gradient of f is 2x comma 2y. So the derivative of this with respect to x is 2x. Y is assumed to be a constant. The derivative of this with respect to y is 2y, because we're assuming x is a constant in that case. So that's how we get 2x and 2y. So let's see what this is. This is a paraboloid, a circular paraboloid. So something like that. And then there's the z-axis, there's the x-axis, the y-axis. Let's say you go 1 unit here, and then 2 units. So we're going to end up with 1, 2, and then this is going to go up to 5, because 1 squared plus 2 squared equals 5. So this is the point 1, 2, 5. 1, 2, 5. And then if we go from this point in this direction, in the x direction, what does that mean? What is the slope? So the gradient of f at the point, let me put the coordinates 1, 2 there. So that point is the point 1, 2, of which we have the point 1, 2, 5. Yep, that's this point up here. And the gradient at 1, 2, the gradient of the function at 1, 2 will be, well, if x is 1, that means 2x is 2. And if y is 2, that means 2y is 4. What does that mean? That means that if you walk in this direction towards us, you're going to be climbing up on the surface at a rate of 2, so which makes sense, at the rate of 2 units per unit, 2 vertical units per horizontal unit coming this way, which makes sense because the farther away you go from the origin, the more you're going to climb up. So if you're at this point and you go in this direction, you're going to get away from the origin even farther from this origin, which means that we're climbing up. So that means we're going to go up. This is a really hard picture to draw. I mean, it's hard to draw how to go up from here in that direction. Oh, I know how to do this. Go up this way. Yep. So we're going to go up to here. And the slope at that point, going up to here, will be a 2, a slope of 2. On the other hand, if you go up in this direction, notice that if I try to match the surface, we're going to go way, way, way up here. The surface, I have to extend the surface, which means that if I want to connect those 2 points, we're going to have a way, way larger slope. And that explains why we go to 4. If you go in this direction, in this direction, in the direction of the positive x-axis, starting at this point, we're going to climb up at a rate of 2. But if you go in this direction, then we're going to climb up at a rate of 4. And you may be thinking, how is that not, isn't it, I mean, this is pretty circular. Isn't the rate supposed to be the same? And the answer is no, because of the point we picked. We picked 1, 2, which is off center. If we were starting at 1, 1, yes, things would be pretty symmetric. But 1, 2 puts it off center, which means we're already more towards the right, which makes this shape steeper. Yeah. So we have to pay close attention to what is going on here and understand what is going on. So that is the gradient. The gradient tells us the slopes going in one direction, x direction, and in the y direction. And that's it. That's essentially what the gradient does. Let's do a quick example, a second example. Example 2, let's say z, notice that I'm using a different notation. Instead of f of xy, I'm calling it z, same difference. X squared plus xy plus y squared, okay? And what is the gradient? The generic gradient would be the derivative of that with respect to x, 2x plus y, 2x plus y, comma, and then, well, the derivative of this with respect to y is 0. The derivative of that with respect to x is, rather, with respect to y is x plus 2y. Yep, and the derivative of that is 2y. So in this gradient, the 2 variables are involved. In this gradient, one of the variables is involved in each one of the coordinates. It varies, depends on the function. So this is some kind of surface. I'm not gonna try to draw that right now. But let's still look at the same point. So not this surface. This is, example 2 is not this surface. It's some other surface. And what happens if we go at 1, 2? So plug in 1 for x, 2 for y. That's the point. Same point, but different surface. So when x is 1 and y is 2, we get 4, comma. When x is 1 and y is 2, we get 5. So what this means is that wherever we are at 1, 2, actually we know the output, because if you plug in 1, 2 into this, we're going to get 1 plus 2 plus 4, 7. So we would be at 1, 2, 7. So there's going to be a point, which is going to be 1, 2, 7. And if you go in the x direction, you're going to go up by 4. So that's pretty steep. And if you go in the y direction, you're going to go up by 5. Yep. So this is in the x direction, this is in the y direction. So kind of like this. There we go. And this is going to be way steeper than going in this direction. So that's what the gradient does. gradients do not work only on 3 dimensions or two inputs. You could have, so this is example 3. It's going to be a super simple example. Let's say you have w equals x plus 2y plus 3z. So this is not a plane. This is a function in 4 dimensions. So it's going to be some kind of a solid. So what is the gradient? Can we do the gradient? No problem. The gradient of w will be, okay, derivative of the function with respect to the first variable. We're assuming that we are going in alphabetical order x, y, z. So x is our first variable. We're assuming that all along. X is first coordinate, y second coordinate, z is third coordinate. So the derivative of this with respect to x would be 1. The derivative of that with respect to y would be 2. The derivative of this with respect to z would be 3. Whoops, 3. There we go. Yeah. So that is the gradient. That is not a v, kind of looks like a v. It's a gradient of w is this. Yep. So if you increase x by 1, the function is going to increase by 1. If you increase y by 1, you're going to increase w by 2. That's what this tells us. If you increase the z value by 1 still, we're going to increase the output by 3 because we're going to weight the z more. That's what that is what this is telling us, how much the x and the y and the z are contributing to the output. So back in our example 2, this is telling us that at that one point, mind, because that changes from point to point. At this point, the x contributes 4 units while the y contributes 5. The change in y contributes 5. The change in x contributes 4 units in the vertical direction. Here we mean in the w direction. Okay, so now we are ready for the directional derivative. Directional derivative. Okay. This looks very restrictive in my opinion. To be able to only do derivatives in the x direction and the y direction, what if I want to go in the 1-1 direction or 1-2 or 2-1, or what if I want to go this way? Oops, this way or this way or this way. Why do I have to go x and y? You know, because perhaps I would like to know, well, what is the slope if I go in the middle, or maybe this way? Those are questions. I don't know. I mean, we will know right now. Okay. So in order to get to that point, and let me explain this a little differently again. Here's my little surface, x direction, y direction. So this kind of gradient, this is not the right dimension, but assuming there were only 2, tells me the slope down this way, down that way, or up, down, whichever way. But what if I want to go in this direction? What is the slope here? That is what we are trying to answer with directional derivatives. Okay, let me talk about averages for a moment. Averages. So let's say you have two numbers, A and B. A and B. So given A and B, the average, as you know, is half A plus half B. That's the normal average, where we are weighing each one of the outputs, the A and the B, or the inputs, the same. This is the same thing as A plus B over 2, which we already knew. What if I wanted to weight this guy more? What if I wanted B to have more of an influence on the average? That would be a weighted average. So a weighted weighted average of one kind would be, let's say, 1/4 A plus 3/4 B. So I want B to weigh 3 times as much as A, and that causes this to happen. So that means that B has more of an influence on this measure of A and B. sometimes, many times, we want to do that. We want to, on purpose, put more influence on one of the inputs versus the other. Yeah, depending. And so if we have two vectors, in two directions, actually two slopes, yeah, here and here, in the x direction and in the y direction, and two slopes from a point, I want to go perhaps in, well, if I want to go in the middle, I want to give the same amount of weight to this guy as to this guy. So somebody may think, well, that means that we can multiply by 1/2 and 1/2, and that will do it. There's a problem with that. We want the vector that goes 1, 1 doesn't have a length of 1, has a length of square root of 2. So this vector is longer than 1 unit one way and 1 unit the other way. In other words, if we add 1 plus 1, we're going to be adding those two vectors, and we're not going to be averaging them. We're going to be adding them, and we want to average them. So the way to, with vectors, the way to do that, to compensate for this addition that is more than 1 is by actually using a unit vector. I guess I said it in a long way. When we have a direction, the direction of the derivative should be unit vector. If it isn't unit vector, because we can give a direction that is not given with a unit vector, that's okay. What we have to do is account for the extra length that we may be getting. Yep. So here's the definition of directional derivative at a given point. Okay, so the directional derivative of z equals f of x, y, and the direction u, so this is a vector which is going to be equal to u1 comma u2. Yep. Is, so the notation we use is derivative in the direction u of f, and that will be u dotted with the gradient of f. And why dotted? Because remember what this means. This means u1 comma u2 dotted with f sub x comma f sub y. And by dotting it, we're actually giving the proper way to each one of the derivatives, x in the x and the y direction. So this is going to be really an average, u1 f of x plus u2 f sub y. Very similar to what's going on here. If we go and multiply 1/4 times a plus 3/4 times b, we're getting an average, we're just putting more weight on this guy. So if we have a vector that where the u2 is bigger, and so that means that the y is bigger, that means that the vector is more towards the y, then we want to put more weight on that second slope versus this first slope. So this is really an average, a weighted average, where we're putting, depending on those two numbers, more weight on one versus the other. Now there's a catch though. We're going to assuming u is a unit vector. Just like here with the averages, we got to make sure that the two numbers the two coefficients add up to 1. Here, we want to make sure um, that we have a unit vector because that is sort of equivalent to having the two of them adding to 1. Now, be careful. A unital vector does not mean that the components add up to 1. If you have the vector, so this is a warning. If you have the vector a half comma a half, the magnitude of that is not 1. It would be the square root. Let's find that out real quick. The square root of 1/4 plus 1/4 because we squared the 2. So that is the square root of 1/2, which is really 1 over the square root of 2. And that is not 1. So yes, we have to make sure those are 1 as a magnitude, not the component. So there's a difference between, and the reason is because we are putting some direction, some dimension to this. You know, it's not just two x's that we're adding together. We're adding a portion of x and a portion of y. So we have to account for the 1 differently than we account for 1 here, 1/4 plus 3/4 in a regular one-dimensional space. So in 2 dimensions, there's an angle that is taken into account, and that causes those numbers not to be to add up to 1. Oh, you guys know the unit circle. All of the points on the unit circle are unital, 1 over the square root of 2 comma 1 over the square root of 2. So this works well as far as using it for a vector. And by the way, this is for a directional derivative. This is 1 over the square root of 2, 1, 1. So 1, 1, the magnitude of 1, 1 is 2. Rather, the square root of 2. If we divide by the square root of 2, then we got a unital vector. And that happens everywhere. Here, when you have 30-degree angle, you got square root of 3 over 2 comma half. Well, which if you factor out the 1/2, you get square root of 3 comma 1. This is a unit vector. Yeah, because if you square this guy, you get 3, square that, you get 1, 3 plus 1 is 4, square root of 4 is 2, that's why dividing by a half, or dividing by 2 rather, makes that a unit vector. Okay, so let's do example 4. Okay, so there's going to be 3 parts to this. Actually, I'm going to put the A after. F of x, y is going to be x squared plus y squared. So our circular paraboloid that we did earlier. Okay. What is the slope? What is the slope in the direction 1, 1? In the direction 1, 1. What is the slope of that surface on that direction? This is going to be labeled A. Oh, there's more. I have to say more. At the point, the same. I want to use the same point we had earlier on our example 1. Yep, on our example 1 back here, we had our point 1, 2. Yep, I didn't spell it out. Oh, there it is. Yeah, 1, 2. Yeah. So this question is not quite finished. What is the slope in the direction 1, 1 at 1, 2? Yes. So there's our picture. I'm going to just draw a new picture. And then there's 1, 2, and then we got 5 going up. All right. If you go in this direction, example 1 told us if we go in this direction, x direction, the slope was 2. Remember? It's back here. 2. If you go in this direction, on the other hand, if you keep going to the right, the slope is 4. Now, this should be just 1 unit and 1 unit. Yeah, what happens is that you go up by 4. The slope is 4. So in this direction, you go up by 4. In this direction, you go up by 2. Well, what happens if we go 45-degree? What is the slope? So if we were to do this, if we were to go up this way, what would be the slope going that way at that point? That's really, really easy. Okay, so from example 1, we know that the gradient of the function at 1, 2 is 2, 4. So this is our direction. The directional derivative um, of the function at 1, 2. So this is the direction 1, 1. I'm gonna say direction 1, 1, but that is not 100%. It is correct, but there's some adjustment we have to make. So to make things simple, what we do, notice that I'm leaving a space here. We're gonna do 1, 1 dotted, which is the direction, dotted with the gradient, 2, 4. I'm missing a factor here. I'm gonna put that in a moment. And remember that that product is just 1 times 2, 2 plus 1 times 4, 4. So that's really 6. Now, the reason why the slope is not 6 is because this is not a fair average. A fair average should be one in which we are taking a unit vector. This is not a unit vector. So we're just adding essentially those two numbers to get 6. But we're not taking into account that we should add a portion of this and a portion of that, not the whole of each one of those. So what we have to do is multiply by the reciprocal of the magnitude of this. That causes this to be a unit vector. So when I said the direction is 1, 1, yes, but we're not going to use 1, 1. We're going to use 1, 1 multiplied by the reciprocal of its magnitude. So we have to put that into account. Square root of 2, 1 over the square root of 2. So the final exact slope is 6 over the square root of 2. That is the actual slope at that point. That is about 4.2. About 4.2. So it is possible, now let's point this the other way, up. It is possible that if this is, say, 2 units and this is 4 units, then this is going at a higher slope than this and that individually. That's what's going on here. So going in this direction gives us 2, in the other direction gives us 4. But if you go in between, you get actually more slope. Yeah, so the average, when I talk about average, it's not a real average as in one-dimensional average. This is like a different kind of an average. We're putting weight on each one of them in such a way that we actually end up with more than one of the two because they're contributing. So we have a contribution of 4, contribution of 2, and we're adding the 2 together. And that's how we get 4.2. The 2 contributions, of course. Okay, let's do B. What if we go same problem, but different direction? Direction, let's just say 1, 2. Direction 1, 2. So we're going to find the directional derivative of this function, same paraboloid, at the same point, 1, 2. That's a little confusing because the point is 1, 2, but then the direction is 1, 2. So that means that, new picture. So 1, 2. So this is not 45 degrees of the origin. And then we're going to go farther in the same direction. That was just coincidental. So we're going to go, yeah. If this point is 1, 2, 5, we're going to go up this way. And we want to know the slope in this direction. What is how far we're going up? We're climbing up on this paraboloid. Okay, so same thing as before. We already know the gradient. Once you know the gradient, if you're changing directions, all you have to do is multiply by that direction, by the unit vector in that direction. So du, well, let me write this 1, 2. So 1, 2, this 1, 2 refers to the direction. F at 1, 2, which is the point. That is a little confusing. So that is blank 1, 2 dotted with, remember, the gradient in this particular case is 2, 4. 2, 4. So that is going to be 1 times 2, 2. 2 times 4 is 8. So that that product is going to be 10. What I'm missing is that we're putting too much weight on each one of those two slopes. We're putting 2. So we're multiplying that slope by 2 and this slope by 1. That's too much. We're adding too much. This has to come down by the magnitude of this vector. So the magnitude of this vector is 5 because 1 squared plus 4 plus 2 squared is 5. And so 1 over square root of 5. So 1 over square root of 5, or just 10 over the square root of 5. This will rationalize nicely because we can multiply with square root of 5 on top and bottom, and we end up with 10 over 5, which is 2 times square root of 5. So the slope here is exactly that, which is the one we want. 2 times the square root of 5 is about 4.4. So we get even more. Going in this direction is even steeper, about 4.4, than going in 1, 1. Okay, let's do part C, in which the direction will be 2, 1 instead of 1, 2. So new picture. 1, 2. I'm going to be there. I'm going to go up. And we're not going to continue going in this direction. Instead, we're going to go, but we're not going to go in the X direction nor the Y direction. We're going to go more towards the X direction. Yeah, 2, 1. So where are we going? What is the slope at which we're going to climb up? Well, the gradient. So the derivative in the direction 2, 1. Now, a lot of books are going to disagree with me, and that is fine. A lot of books are going to say, well, this vector has to be unit vector. So many will say, and they're right, I'm not saying it, direction must be unit vector, and that is not a unit vector. Let's say f of 1, 2 as before. I'm a little more liberal than that because this is a direction. As long as in the answer you take that unit vector into account, I'm okay. Unit vector. So in the answer, we're going to have 1 over the square root of 5, and that accounts for the extra length of this vector. This vector is longer than 1. Square root of 5, just using my calculator real quick, is about 2.24. So this is way longer than 1. This vector is way longer than 1. It's 2.24. So we have to divide by that to account for the extra length. And then we have, yep, 2, 1. But I like to set it up this way. 2, 4, because that is the gradient. Remember, that is the gradient of the function at 1, 2, 2, 4. I think this makes things a little more clean as long as we take into account the extra length of the vector. So let's do this. 2 times 2 is 4. 1 times 4 is 4. So we end up with 8. So that is 8 over the square root of 5. That is the exact slope in this direction, which is about, it's not 10 over the square root of 5. And by the way, rationalizing this does not simplify it too much, so I'm just going to leave it alone. I'm going to do real quick the math. 8 divided by square root of 5 equals about 3.6. 3.6. This is the answer we always want, but I just want to have an idea of what's going on. So this direction 2, this direction 4, this direction is more than 2. Why? Because the 4 is adding up to it. So here we get about 3.6. Remember the 45-degree angle, that was A. And now I forgot what it was. So it was about 4.2. Yep. So that was about 4.2. And then this direction gave us about 4.4. I still remember. And 4 again, and 2. Now, so let me draw a picture. So in the x direction, we get a slope of 2. In the y direction, we get a slope of 4. And you may be thinking, well, shouldn't we get numbers in between? No, because they add up, they add one onto the other. So you go 2, and then you climb 2 this way, but then you climb 4 this way. But they don't add up exactly to 6 because we have to take into account, if you go 2, so this is supposed to be 1 unit. This is misleading because this is longer. Let's make it about the same. There you go. 1 unit. There you go. Yeah, if you go 2 and 4, if you get to this point, sure, you're going to get 6. Yes, but we want to go the same distance. That's the deal. So we don't want to go 6. We want to take into account that we want to stop here. If we were all the way to 1, 1, all the way there, yeah, the slope would be 6. Well, see, that's the rise would be 6, but we're not taking into account that we want to go only 1 unit far. 1, 1, 1. There we go. So that's why here we get 4.2. If we kept going all the way up to 1, 1, yeah, we would get 6, but we get instead about 4.2. So the slope is, well, let me write it over here. Slope is about 4.2. If we go 1, 2, 1, 2, so if we go, actually this point, 1, 2 would be up here, way up here. I'm just making it smaller. I'm using similar rectangles. So instead of going 1, 2, I'm going a half 1. So the direction is here. So if we were going 1, 2, that was example B. Yep. It would be 1 of those and 2 of those. So the answer would be 10. So we were actually going 1 and 2 way up here. So 1 unit and 2 units, we will get up to 10 units above this point, above this one, 10 units. But that's not fair because we have to take into account we want to go only 1 unit away from where we started. So when you take that into account, that's why we have to divide by the square root of 5. And that gives us 10 over the square root of 5. And that's how we get about 4.4. And similarly, going in this direction, so that would be about 2, 1, so about here in this direction, but we want to stop there. We would get a slope of 8 over the square root of 5. It is a coincidence that we're getting square root of 5 in those two because I'm using the same numbers, 1 and 2 and 2, 1. Had we been using other numbers, then we wouldn't get square root of 5 necessarily. Yeah, which is about 4 point, so that was 4 point, no, 3.6, 3.6, about, approximately, yes. So that is what's going on. The directional derivatives take into account those two, they add them together, but then we have to, adding them together would take us all the way out to a point far away, but then we have to bring them back. And that's why we have to divide by the magnitude of the direction vector. Yep. So another thing we have to realize, or one question we can ask is, okay, I know which way, you know, it is cool to know now, because one of the frustrations I had is, well, if you go in this direction, you get an answer. If you go in this direction, you get another answer. And the initial question is, well, what if I want to go this direction? What is the answer? And then we just realized how we obtained that answer. That makes sense. But then the next question is, well, if I'm at a random point here, fixed but random point, which direction will give me the most slope? We know there is going to be a direction that is going to give us zero slope. If you go around this way, you're going to get zero slope going up, I mean, relative to the z-axis. But which one gives us the maximum? And the answer is not obvious, because it's not just 1, 1. It's not up. Depending on where we are, the direction of maximum slope varies. So direction of maximum slope is a question we want to answer. All right. The dot product gives us maximum values when the two vectors we're multiplying are parallel in the same direction. We get minimum, the dot product, if the direction is opposite, well, same direction but opposite way. So maximum, minimum. That is the whole point of the dot product, in my opinion, in physics. Because in physics, it is very, very important to know when things are parallel or perpendicular. And dot product and cross product carry that kind of information, the perpendicularity and the parallelism of different vectors. In fact, the dot product gives us 0 if the two vectors are perpendicular to one another. Okay. So again, the dot product, the more parallel they are, the vectors that we're multiplying together, the more of it we're going to get. We get maximum. Yeah. Because the dot product, one of the things we learned is that if you have two vectors, v dot w, that is the magnitude of v, magnitude of w times the cosine of the angle in between them. And so if the angle is 0, you get 1, which is as much as cosine can be. So this is bounded. If you fix v and w, the length of v and w, this is bounded by cosine. And you guys know cosine. Cosine can be the most 1. So the maximum we can get is 1 because of this cosine, because of this equation. The minimum we can get is -1. And that happens with 180 degrees, so when the vectors are opposite. And we get 0 at 90 degrees. This is a cosine function. All right. So the maximum will happen when the gradient and the, okay, so sorry to interrupt myself. The directional derivative of a function is equal to u, assuming u is unit. Unit. If it is not unit, then you have to account for it. Dotted with the gradient. Well, the maximum of the dot product will happen when those two are parallel, which means that if all you have to do is take the direction of the gradient, and that gives you the maximum. So remember our example. Let's do a new example. This is going to take a little longer than what I anticipated, but that's okay. This example is worth seeing, this common example. I'm just looking at to see what the next example should be, example number 5. Say f of x, y is 25 minus x squared plus y. Okay, so y is a straight line, diagonal 45-degree angle line. This guy is a parabola opening down. So I really like the picture of this. What we end up with is a parabola opening down, but going up. So this is sort of a cylinder. I don't know if it's still a cylinder, but it is sort of a cylinder. It is a surface. So this could be the z-axis going down through the center of this parabola. And in that case, somewhere here, we're going to end up with the x-axis going this way, and then the x-axis, and then the y-axis is going to go this way. And this is just going to continue going down. Yep. There. Yep. So this origin is inside of this sheet, and this sheet keeps going up this way. So that doesn't stop. Okay, so this is this new function. Okay, let's go to 1, 2. 1, 2, somewhere in there. So just so we know, f of 1, 2 is going to be 25 minus 1 squared minus 2. That's 3, so that's 22. Okay, so we're going to be way up here at 1, 2, 22. So this point here is going to be 1, 2, 22. Because if you plug in 1 and 2 into this function, 1 and 2. Oh, wait a minute. I said that wrong because we're adding 2. So 2 minus 1 is 1. That's 26. Sorry about that. Boy, that was that was sad to subtract. Yeah, sorry. I'm embarrassed to do this on YouTube, but oh well. So what did I say? 24 plus 2, 26. Yep, 26. There we go. Okay. So this is 26. 1, 2, 26. What is the gradient at 1, 2? So this point down here is 1, 2. I don't want to put the coordinates there because I might have to draw more pictures, more vectors up here. So I don't want to put too many things in that picture. So the gradient of the function at 1, 2, well, if we find the gradient first, we end up with negative 2x, comma, 1. And then we're going to plug in, this symbol means we're going to plug in 1, 2. Let me write it again. So 1, 2 equals negative 2x, comma 1, because the derivative of this with respect to x is negative 2x. Derivative of all of this with respect to y is just 1. And we're going to plug in 1, 2. Huh. So that means we're going to end up with plug in 1 for x. So that is negative 2, comma, plug in 2 for y, but there's no y, so it's just 1. So negative 2, 1. What does that mean? If we go in the x direction, we're going to go down. So we're going to go down by a slope of negative 2. So if we go in this direction, we're going to go down, which makes sense. The parabola is opening down, so that means we're going down. If we go in the y direction, the slope is going to be 1. So yeah, that is interesting. Yep, it makes sense because we're going to be higher up there. So 1 and then negative 2. So in this direction, we're going down. In this direction, we go up. In this direction, we go up by 2 also. Yeah. So this is the point. up by 2, down by -2, up 1, down -1, if you go in the opposite direction. So somebody may say, well, so that means that is the steepest it will ever go. Not necessarily. Which direction is the steepest? If you want to climb as steep as possible, which direction should you climb? This is, let me change gears a little bit here. Let's say you are in some random surface that looks like a mountain, and you are here. Yeah. Which direction gives you the highest slope? Well, it appears that if you go up this way, that's going to be the highest slope, lowest, opposite. And if you go perpendicular, you're going to go 0 slope. Okay, so pretend this is a mountain. If you walk around the mountain without going up or down, then your slope is 0. You're not changing the level. You're still on the same level. Height. If you go in this direction, we go up by 2. This direction, down by 2, up by 1. So it may seem like we are all set, but no, because we have a maximum direction. And what is the maximum direction? Yeah, since we did not get 0, a slope of 0 here, this cannot be the maximum direction because those two are going to be perpendicular on the floor. Not here, but on the floor, they're perpendicular. Yeah. So the direction of maximum, since this is the gradient, the direction of maximum slope is going to be in the direction of the gradient. So the gradient is -2, 1. It's a vector, -2, 1, which is going to be, let's see, the x has to be -2 and then 1. Yep. So if we go in this direction, which is going to be about there. So if we go this way, that's where we're going to get our maximum slope, which makes sense because we're going to be climbing the parabola on top of climbing the y. See how we go up this way? It's a double climb. This slope plus this slope. There's 2 slopes to get in this direction. So the direction of maximum slope or rate of change, whichever way you want to say it, is -2, 1. It is the gradient itself. Why? Because the dot product parallel same direction gives you the maximum. Yep. And then the next question is, well, what is the slope? What is the slope? With slope, okay, so we compute the directional derivative in the direction -1, 2 of the function at 1, 2. It's a little confusing to keep using 1, 2 because then the 2's and the 1's keep showing up. So that is going to be the dot product -2, 1 times the gradient of the function at that point, which is -2, 1. Notice that I left a space here because we're missing a factor. I want to put the factor after. So this is going to be -2 times -2, 4 plus, we're doing the dot product, 1. So that's going to give us 5. And as you know, that is too much because we are taking two of those slopes and one of those slopes, and that's too much because we want to stop at one unit out. See, so we want to stop at 1 unit out no matter what. So that's why we have to simplify, well, reduce this by a factor of 1 over the square root of 5, which carries down here, which carries down here. So, and then we simplify down to square root of 5. There we go. So, which is about, I already figured this out earlier. I forgot what it was. 5 square root is about 2.4. It's really many more digits. I don't know, 2.23, so 2.24. about 2.24. This is the number we really want to keep as final answer. I just want to have an idea. So if we climb this way, the slope is 2 because the slope was -2. If we climb this way, it's 1. If we go in the maximum, in the hardest possible way to go, we're going to go in the direction -2, 1, which is towards the y-axis. And we're going to have a slope of exactly the square root of 5, which is about 2.24. So the slope is going to be higher than if we were going here. We're going to go higher. Yeah. Yeah. I just want to show you real quick kind of what's going on. I don't know if this will work. Okay, so pretend this is it. So if we go up this way, the slope will be 2. If we go this way, -2, which makes sense. This way, the slope would be 1. But then there's here a harder climb from this point, and that would be a slope of 2.24. I hope this kind of shows reasonably well on the YouTube video. Oh, and there's one more thing. Once you have the maximum, let's go back to the picture of the dot products. So maximum, minimum. So the minimum will be on the opposite direction, and it's going to have the, so if you go in 2, -1, which is totally opposite, this direction, you're going to get the minimust. That's going to be the fastest way to fall. If you put a coin here, that's what it is going to go this way, because that is the fastest way it can go. And it is the least resistance. The coin is going to, if you put a coin here, it will go exactly this way. It's not going to go down this way or this. It's going to go exactly this way. Or a ball, if you put a little ball, let it roll, it will roll down this way. Which is the direction where we have 0. Because when you have a surface, any kind of a surface, there is going to be one direction. So this is slanted. So this is higher and this is lower. There's going to be one direction where we're going to maintain the same slope. And the question is, or not the same slope, I meant the same level. So new picture. This is kind of exciting to me. I don't know about to you, but so there's going to be some direction where we're going to not go up or down. So the question is, what's the direction in which we're going to maintain? So if this continues and you go around, which direction is it going to be where we maintain the same level? Well, the gradient of the function at 1, 2 is -2, 1. So if you go in the perfect so that is this way, because we end up with -2. I just got a little -2. Oh yeah, that's this is this way. Yeah, that's the maximum. Yeah. If you want to go on 0 level, 0 rise, then you have to go on exactly the perpendicular to this, which is going to be, let's see what direction that would be. 1, 2. Will that? Yeah, because all you have to do is flip those two. You just got to find a vector that whose dot product with this one is going to be 0. So -2 times 1 is -2. 1 times 2 is 2. When we add them together, yep, sure enough, we get 0. That is a coincidence. Yeah, that's coincidence that we get 1, 2. That really has nothing to do with that. So if you go in the direction 1, 2 on the floor, so if you go 1, 2, you're going to end up at a point that is going to be, well, at that, not at 1, 2, but if you go, because this keeps changing, as you go around, this goes around. So at one, if you go in the direction 1, 2, here, you're going to end up with points that are at the same level. But once you get to this point, you might have to change the direction again to keep up with the level. You might have to be turning. It's like if you're on a mountain, pretend this is a top view of mountain, you know, so this is the top of the mountain, and then you're here. You might want to go around to keep the same level, so you come back to the same point without going up or down. Well, if you start here, you got to go in this direction. But once you're here, you got to go in this direction to keep up with the level. So that's what I mean. It's not necessarily that you have to go 1, 2, and you end up with the same level. No, no, no. 1, 2 initially, but then once you are at a different point, you have to change the direction again to keep up with the level. And that's what I mean here. This is a top view. Pretend you're on a mountain, you're here, and you want to go around the mountain. What you do is go in this direction initially, but then once you change your position, you got to change the direction to keep up with the level. All right, hopefully this is insightful, and we'll stop here.